In this video, we'll be talking about Kirchhoff's circuit laws. Kirchhoff's current law states that at any node in a circuit, the sum of the currents entering equals the sum of the currents leaving. If we imagine water flowing through a pipe junction, then everything that enters the node must leave the node. Kirchhoff's voltage law states that the sum of the potential drops around a loop equals the sum of the potential rises. This means that any time there is an increase in potential, there must also be a decrease in potential to counteract it. If you start at one point in a loop and travel all the way around back to where you started, you should have the same voltage as you did before you went around the loop. In our first example, we have a circuit and we'd like to find each of the three currents indicated, I1, I2, and I3. None of the components in this circuit can be combined as nothing is in series or parallel. The circuit has two independent loops, ABEF, the loop on the left, and BCDE, the loop on the right. ACDF is the outer loop, the entire outside of the circuit. The circuit has two nodes, B and E. However, only one of these can be independent. When we use the voltage law for ABEF, we'd like to arbitrarily pick a direction for the current traveling in the loop. We'll say that clockwise is going with the current. In this case, I1 moving through the 20 ohm resistor will be a voltage drop. I2 moving through the 10 ohm resistor will be a voltage rise. The 10 volt battery in the middle will be a voltage drop, and the 10 volt battery at the bottom will be a voltage rise. This equation will simplify down to 20I1 minus 10I2 equals 0. For the second loop on the right, we'll again say that clockwise is the direction the current travels in. I3 is a voltage drop, I2 is a voltage drop, the 20 volt battery is a voltage rise, and so is the 10 volt battery. This equation simplifies down to 10I2 plus 5I3 equals 30. Loop ACDF, the outer loop, will just be the equations for ABEF and BCDE, the left and right loops, summed. So, the equation for ACDF is dependent on those equations, and there's no need for us to consider it. We need one more equation to account for our three unknowns. Using the current law at B, we notice that I1 and I2 are entering the node, and I3 is leaving the node. If we consider point E, then we notice that we will end up with the same equation. I2 and I1 are leaving, and I3 is entering. Were we to multiply this entire equation by -1, we would end up with the same equation that we got for point B. Now that we have three equations, we can solve them using any technique we like. First, we can add the first two equations to obtain the following: 20I1 plus 5I3 equals 30. We multiply the third equation by 10, then we can add it to the first equation to cancel out the I2. We multiply the first derived equation by 2, and then we can add that to the second derived equation to cancel out the I3 term and end up with a value for I1 being 0.857 amps. At this point, it's simply a matter of plugging I1 back into other equations to find I2 and I3. So, we can find I3 being 2.57 amps and I2 being 1.71 amps. In our second example, we would like to again find the currents in the circuit. Here they're not labeled, so we'll have to do it ourselves. We won't worry about directions, because if we get the directions wrong, we'll just end up with negative current. We'll let I1 be the current moving up through the 12 volt battery, I2 will be the current moving down through the 15 ohm resistor, and I3 will be the current moving down through the 25 ohm resistor. Using the voltage law for the left loop, we can immediately determine I3 as being 0.48 amps. Using the voltage law for the outside loop, being around the entire circuit, we can derive I2 being 1.2 amps. Using the current law for the top node, I1 is entering, and I2 and I3 are leaving. So, we can plug in our known current values to find that I1 is 1.7 amps. Because each current that we have found is positive, the directions that we picked for the currents are correct.